And a line that is perpendicular to a radius is tangent to the circle. Wolfie?
Basically it's the same thing except it's reversed. Like,
So what is that called?
so converse.
Yes, they're converses. Okay, 8-3 is the converse of 8-2. So if you have a tangent, then it will be perpendicular to the line, or to the radius that's drawn at the point of tangency. So basically that's the if. So if you have line, and I didn't put enough information there to, let's call it line L, I guess. So if you have line L, then it's perpendicular. And then the other one is if you have perpendicular, if it's perpendicular, then it's a tangent. Okay, that's just my short, you don't have to write that down, but they are converses of each other. So if you're given a tangent, you know it's going to be perpendicular to the radius that goes to that point of tangency. And if a radius is perpendicular to a line, then it must be a tangent. Okay? Common tangents could be internal or external. I have a lot of time left, but I do want you to work on some of these on your own. So, why don't you guys actually do the oral exercises to try to become more familiar with the definitions, and then we'll work on this more on Monday. So normally we do those together, but I'm gonna have you guys do the oral exercises. So all of those 1 through 16.
Do you have to write them down, or can we just talk about them?
I'm letting you write them down, please.
What?
Nice try, Morgan. Glad you clarified on that. Okay? Have a good day.
Thank you.
What's today? Today's March. Oh my goodness. Good
In
job.
March for like
Oh
1
yeah,
week.
it's the 11th. I forgot it was your birthday.
You're 18.
Kramer used to do that. What are you know to do?
Like running to the line.
I remember Kramer used to do it all the time. He goes, I'm going to McDonald's.
Luckily, we're done early today.
Well, probably why we have that so strict now.
It's so hot in this building.
Really?
Yes.
It's
Like
obnoxiously
kind of hot in here.
Obnoxiously hot. It's really weird though because there's certain spots that are really warm and then really cold. I feel like I'm like really cold and flashing. I had a question on the last slide.
Yes, please do get that out.
I'm not sure if I'm right, because that didn't come out very well. It was weird. This angle and then
I definitely did
1
not get
kilogram. And that doesn't make any sense.
You use 1 kilogram of what?
That's what I
I
took.
tried to do number 6.
I don't
Whatever I
think I
got
did.
here, I took and I divided
It's
it.
probably wrong. What did you get?
I didn't get it right. I got like a huge number, so.
Yeah, I got a big number too.
Well, mine's like 1,000 something.
Oh, mine
Yours
was
isn't that big.
280.
That's what I got.
I got 4.9.
Okay. Well, let's just read through all of these and just check. Number 1A, they were both 53 newtons. B, the Y was 10 and the X was 6. Number 2, is B, C, D, E, and F.
I didn't know if you could circle multiple. It didn't say, because it said which of the following. I don't know, never
Wait.
mind.
Yeah, it
Wait,
doesn't,
can you
it's
read
not
these
very
again?
Yeah.
specific.
Oh, I
but
just circled
you
one.
can circle
Me too,
multiple, yes.
but I was like,
B, C, D, E, and F.
B, C. At least we circled one.
That's
Good
choice
choice.
2, right?
they
Yes.
all the same.
I just
3 was A, B, E, F, and G.
not
Wait.
Which one?
D.
No. So following statements were made about an object, in which case could you conclude that it's at equilibrium? The problem with D is that speed could be, they could be changing directions.
But it's constant.
Yes, but it's a constant speed,
Oh.
and so it could be changing directions.
So if
That's
it,
why, that's the difference between B and D.
so if it said constant acceleration, then you could have chosen it for D instead of speed.
No, if it's constant velocity. Acceleration would mean it would be changing. And so if it's changing, it can't be at equilibrium. Number 4, F1 of X is equal to F2 of X, F1 of Y is less than F3, F2Y is less than F3, and F1 plus F2 is equal to F3. 5, 19.3, 7.1, and 5.8.
I got like 0.15 and 0.20 for the last. I don't know how. I wonder if they did differently.
You're determining the tension in the wire,
Mm-hmm.
so it should be sine of 45 equals 5 over x. So x times sine 45 equals 5, divided by the sine 45. Give you x.
Oh, I know what I did wrong. Okay.
And number 6, you should have 286.5 meters.
Do you think you could show this one on the board?
I got 280.
That's your 80.764.
Okay, even though I closed parentheses, I still got like 0.14.
Are you in degrees?
Yes, I think.
That's what was one, I guess, but.
Yeah, I remember.
I was like, how would I need a picture? I would use a
It's
nail.
5
not
divided by
I
the
was like,
sine
I just
45.
know, I don't know why.
Five
Just
is
not
not.
change.
Which one is it supposed to be? I don't even know.
That was my guess because I.
Alright, a student pulls with 2 large forces in order to lift a 1 kilogram book by 2 cables. If the cables make a 1 degree angle with the horizontal, then what's the tension in the cable? So we'll just, it doesn't look quite like this, but. Okay, of those, forces, which one do we know?
The angle? Oh, that's not. You know the
we know the mass, so what one can we, calculate? What? Yeah, F grav, which in this case is what?
3.
Force 3. So if the mass is 1, how do I calculate the gravity? 1 times 9.8. So that's 9.8. Whatever I was looking at must use 10 for the force of gravity, so if your numbers are slightly different, that could be why. Because they use 10 as the force of gravity instead of 9.8. And so, then what do we know?
Y is 4.9.
Say that again?
Each Y is half 9.8.
Right, so each of these Fy components is going to be half of 9.8, which would be 4.9. And so then to find, we'll call this X, I guess, the tension force, it would be the sine of 1 equals 4.9 over X. So X times sine of 1 equals 4.9. So it's 4.9 divided by the sine of 1. What is it?
280.
Okay. So mine was from using 10, it was 286.5.
I did it different way, that's not.
How did you do it?
Or I just did,
I just need to do a bunch of stuff.
cause I didn't, well, obviously I did it wrong, but I don't know how I got this. I did, I don't know what I did.
Sounds like you got lucky.
Remember I was showing you my calculator? Like, this doesn't make sense.
Yeah, I don't know what you did though.
I just didn't go one more step.
I got the right answer.
Okay. Any other questions about that? No? Alright. Then get your notes, please. And today we're gonna do problems that are not balanced. They're not at equilibrium. They have a net force. So, a force that's exerted at an angle to the horizontal can also be resolved into its components. We were doing that last night with the tension force, putting it into the X and Y components, or mainly just the Y ones we were concerned with. And then we can use those to replace the original force, and that will help us to determine the overall net force of the object, since not all of them are gonna be at 90-degree angles. So we're gonna work through a couple examples of that, just step by step. So this is the same as the net force problems that we did in an earlier chapter. The only difference is that we are adding on the angled forces. Okay, so first example, determine the acceleration of the object that is represented in this free body diagram. So the first thing we're gonna do is find the components of the applied force. So the applied force is at this angle here. So we're going to find the X component of that applied force and the Y component of the applied force using trig. So how would I calculate those? Right, so the sine of 30 would be Fy over 150, or the Fy would equal 150 times the sine of 30, and the Fx would equal 150 times the cosine. And that would give you what?
$75.
75 is the Y. 75 newtons.
129.
So 130, okay. And you might, if they're not exact, you might want to store them because we are going to have to be using them later on. So you want to store them as something that you know or can remember, like X and Y. Okay, and the next step is going to be then to calculate the net force of the object. So, what do we know about the vertical forces? Okay, what are the vertical forces here then?
64 and, no, that's horizontal. 121 and 196 and 175.
Okay, so we have, we can either, let's go ahead and go with calling them positive and negative, just so we have an
Okay.
idea of what direction they're going. So the normal force is positive 121. Then we have the Fy that we just calculated of the applied force, which was 75. Those are both positive, those are both going up, and then we have gravity, which we'll call negative 196 because that's going down. So if I add all of those together, what do I get?
Zero?
Yes, it's balanced vertically.
It's like,
Yes, it's vertically balanced. So then the net force must be horizontal. So we have, again, if we want to call it negative and positive, we had a negative 64 newtons since the friction is going to the left 64. And then we have the X component that we just calculated of 130 newtons to the right. Don't let the ends confuse you. We start thinking of N as north, but it's for newtons of force. And that will give us what?
65.904.
Okay, good. So I'm gonna write 66, but again, you might wanna store that, so if you're gonna store that as like N for net force, that is the net force that we're gonna be using. Okay, then we're going to find the mass, because we need to know mass in order to calculate acceleration. And so mass is the, can be found using the weight equals the F grav, which equals mass times gravity, so we can find the mass that way because we know the gravity is 196. And so that will equal 9.8 times the mass. So mass is gonna be gravity divided by 9.8. And you should get, what,
20.
20. Okay, so the mass is 20 kilograms. And then lastly, we can find the acceleration, which is what they're asking us for to begin with, using one of those equations from Newton's second law. In this case, it would be the acceleration equals the net force divided by the mass. And so acceleration will equal 66 divided by 20. Or the net force divided by
3.3.
and you get about 3.3 meters per second squared. Questions? No? Okay. The next ones are going to be talking about friction. And so when we have friction, and a lot of times when we're moving things, even if the applied force is at an angle, the object is still going to be moving along a flat surface, and so the upward forces are going to be balancing the downward forces. Okay, so we need to know that the normal force will balance with the gravity and also the y component, the vertical component of the applied force. So that's what those first two equations are telling us. And the force of friction is dependent upon the value of the normal force, which is why it's important to know what that force is. And this equation should look familiar to you. We did it back when we were talking about forces. And that's that the friction will equal, that's the Greek letter mu, which represents the coefficient of friction times the normal force. Okay, so we're gonna go through another example step by step, similarly to the last one. A 62 Newton applied force is exerted at a 30-degree angle above the horizontal to accelerate a 12 kilogram box of books to the right. The coefficient of friction between the books and the floor is 0.45. Determine the acceleration of the box. So in this case, we're not given a free body diagram, so we need to make one so we know what's going on here. So, what forces are present?
62 applied.
Okay, and that's at a 30-degree angle above the horizontal. So that's going to be this way. And that's 62 newtons, and we should probably draw in, that's 30 degrees. Okay, what else? That's correct. Right now though, we just want to draw all the forces for the free body diagram.